Hello, in this video I'll be solving problem 39 from section 14.8 of James Stewart's Calculus Early Transcendentals. This section is about Lagrange multipliers, and this problem asks us to prove, using Lagrange multipliers, that the rectangle with maximum area that has a given perimeter little p is in fact a square. And okay, how do we do this? Well, with any problem involving optimization, especially the word problems, the first thing we need to do is identify the things we want to optimize and the constraints that we're given specifically for Lagrange multipliers. So we want to, already right here, we can see maximum area. And so that tells me that the thing I'm trying to maximize is the area. The area of what? Well, it's going to be the area of this rectangle. And so the first thing I'm going to do is I'm going to draw myself a rectangle, and let's give its sides some names. So I'm going to call length and width. And so then with these variables, the area of the rectangle is going to be, I'm going to call it the function a. It's going to be a function of L and W, and this is just L times W. Now we're also given, right here, that the perimeter of the rectangle is just P. Now the perimeter, let me write a function for this. I'm going to call it capital P. This will also be a function of the length and the width, and the reason why is because, well, the perimeter is just the sum of all the lengths of these, but with a rectangle, this side and this side are equal, and then this side and this side are equal. So if we add all of the sides together, we get 2L plus 2W. And we're given that this thing is equal to little p, where little p is that constant they gave us. And so, okay, now with all of these givens, what we want to do is we want to optimize A, because we want the maximum area. And again, we're doing this with Lagrange multipliers. And as a reminder, the method of Lagrange multipliers says, let me write this down. To optimize, say, a function f of xy subject to the constraints g of xy equals some constants, c. What we need to do is solve the system of equations given here. So we're going to take the gradients of f and g, and we're going to set them equal to each other with this Lagrange multiplier, as it's called lambda, and we're going to scale the constraint by that parameter. And then the other equation in our system will just be the constraint. So this is g of xy equals c. And so for us, the system we're going to solve is, well, we need to first calculate what the gradients of a and p are. So let me erase this. First, let's calculate the gradient of a. That's not so bad. So this is just partial a with respect to L, and then partial a with respect to W. And this is pretty easy to calculate because it's just L times W. So partial a with respect to L is just going to be W, and then likewise, the other partial derivative will just be L. Now let's compute the gradients of the perimeter. This is also straightforward. So partial derivative with respect to L, that's just going to be 2. And similarly for the partial derivative with respect to W. So our system is going to be WL equals lambda of, or lambda times 2 comma 2. And then we have, let's label these equations actually. or no, I'll add the labels after I equate components. So we have this, and then we need our constraint, which again, our constraint says that the perimeter is just equal to P. So 2L plus 2W equals P. If we equate components, in the first equation, we get that W equals 2 lambda, L equals 2 lambda, and then 2L plus 2W equals P. And this is the system we need to solve. Let me give these equations some names. And at this point, I think it's wise for me to say that sometimes with these Lagrange multiplier problems, you will need to figure out what lambda is like for that problem. You will need to solve for lambda. It's interesting to point out, though, that in this problem, that's actually not necessary. We can actually get away with finding out what W and L are without having to solve for lambda. And the reason why is because we can see that from 1 and 2, both of the right sides are equal. They're both 2 lambda. So from 1 and 2, we can just set these equal to each other. W equals 2 lambda, but this is equal to L. So W equals L. If we insert this into 3, so we replace W by L in 3, we get 2L plus 2L equals P, or 4L equals P. So L is equal to P over 4. But then, from this equation here, since W equals L, we see that W equals P over 4. Also, and so both of these, the length and the width, have the same length. So our rectangle has to be a square. And actually, now that I'm looking at this, notice how we already arrived at this conclusion immediately from the fact that we got this equation here. So we actually didn't need to substitute or use equation 3 at all. Just from knowing that the Lagrange multiplier condition tells us that this has to hold, when we expand components and equate these, we immediately get that the width has to be equal to the length without knowing what those without knowing what that width and length are. And therefore, well, once we know that our rectangle has to be a perfect square, because for a perfect square, all 4 of the lengths are equal. So in particular, this is equal to this, and likewise, this is equal to this. I'm going to add that as a note for everyone. From 1 and 2, we see that this already tells us our rectangle is a square. And importantly, without needing to find W and L explicitly. And there we have it. In fact, as we have found right now, to get a rectangle with the maximum area subject to it having a fixed perimeter P, the only way to attain that is to make our rectangle a perfect square, as desired. Okay, that's it for this problem. If there are any questions, please feel free to leave a comment. Otherwise, I'll see you all in the next video.